Well, for you, that's what you think.
Yeah.
George. We're getting started.
But my thing is checking the traffic, but it can't happen, so I
All right, guys, we're getting started here. I'm gonna go over this one thing, and then it should probably take 10. Guys. I'm gonna go over these last two problems, and then we're gonna have a work day for the rest of the period. Okay. So the first one on 26 says take a segment which starts at the origin. Here's the origin.
Super.
And it ends at the point HR. So this is the point HR, which means this X value is H and the Y value is R. Any questions yet? Hopefully not. Pretty easy so far. Okay. Now it says we're going to take this segment and revolve it around the x-axis. So what shape is it going to make? A cone. To make a cone. So, okay. So let's examine one of the slices. Okay. Here's a slice. So I'm going to envision this carving out a circular disc around the x-axis. So if I draw this. All right, what's the thickness of the disc? dx, a small little change in x. And that tells me that I really want my radius to be having x's in it, right? Because my integral is going to be with respect to x. So what is the radius? It makes more sense if I draw it up here.
Reading that question, isn't it just the line segment that's being revolved? Or is it the area below?
Well, I guess if you revolve just the segment, it would be the like the top of the cone, not including the bottom. So then you can talk about how much volume is contained in the cone. That's a good point. Yeah, this wouldn't be like necessarily the way it's phrased. It's not necessarily a solid. I guess it says volume of the solid, so you might be like, oh, is it really a solid? But you get the idea.
Yeah.
I meant for it to be like, okay, I guess that if I rephrase this, it would be, take the region bounded by this segment, and then this segment, and the x-axis.
Yeah. You know what, J-Ho, this might be the best disc I've ever made. It's pretty good.
That looks pretty good.
Yeah.
Who thinks they know what the radius is? Anyone?
8? Or
Laura's got it?
Is it R divided by 2? Or not R, like however 8 is divided by 2.
Isn't it just
Maybe you're thinking that because I happen to draw it right here, but I could have just as easily drawn it over here. But you're on the right track as far as it has to depend on H. It depends on H and it depends on R. Alyssa, you got it?
You take into like the equation of the line, it's like x over 2, or like whatever. I don't know. Never mind.
I agree. You got the main idea, which is I want the equation of this line. Y equals, well, it crosses the y-axis at the origin, so it's just going to be y equals mx.
Yeah.
What's the slope of that segment?
R over H.
So the equation of the line, we all agree that that's the equation of the line?
Yeah.
Y equals the slope times x, and the slope is r over h. Right? So that means that my radius is the y value of this point, right? So the radius is r over h times x. Do we feel okay about that?
Mm-hmm. Yeah.
Okay.
Why
So
isn't it times 1/2? Because wouldn't the be like
where are you getting the half from?
like because of you're not doing like the whole diameter, you're just doing like it's
bear in mind that this is, we're revolving it around the x-axis, so this disk looks like this. So if you said like, say, oh, they're gonna be, I mean, if you said that we're gonna make the cross sections be circles that span from, say, this to this, then you could have little circles inside there. That's possible. And then, yeah, the radius would be half of the y value, but when you revolve around the x-axis, the y value of the function is the. Sorry. Okay,
Well, like
so
if you were gonna find the diameter, you'd multiply by 2, because the radius is the y value.
the diameter. So that we've certainly done problems where you've got a curve of some kind, and you go, oh, the cross sections are semicircles perpendicular to the x-axis, and then the little sections look like that, and then the radius is half the y value. But if you're revolving around the x-axis, then the radius is going to be your y value. So, okay. What's the volume of this disk? Well, pi times the radius squared. So the radius is r over h times x. Does that make sense? Times the thickness of dx. So that describes the volume of this disk. And then if I want all of it, if I want the entire volume, I have to integrate.
Hello, Gabe.
Thanks. Yeah.
Dose.
You pass those to Hannah and Laura. What are the bounds of integration?
0.
From 0 to h. Okay, this part's
Angry.
a little tricky. You got to remember that r and h are just numbers; they're just constants. So they don't behave like x's. They behave like, for example, r could be 3 and h could be 7. That's how they behave. So, what should I do with this?
Expand it?
Expand or square it, and then
Square it.
I'll have an r squared over h squared, and then a pi, and those guys can all live outside the integral. Do we feel good about that?
Wait, why can the r squared in these? Oh, the constants.
Because they're constants, yeah. So like if this had been a 3 and a 7, we'd have 9 over 49, and we could take that out of the integral. Then what's left over inside the integral is just an x squared. Okay. We're okay with that?
Yes.
So this guy is still a constant, pi times r squared over h squared. We can integrate that guy now. One third x cubed, evaluated from 0 to h. All right, now, again, don't be afraid. H is just a constant. You just plug it in. So what happens when you plug in h?
Becomes 1/3 cube. Ooh, and there's an H.
So you get a 1/3 h cubed minus 0. And so what's going to happen here? We got this times this. So I got the 1/3. There's a pi. And there's an r squared. And then h cubed divided by h squared is h.
Whoa.
And that's the famous cone volume formula. So,
Yay.
they're in there in case it wasn't clear before. That the reason we chose r and h was r is the radius of the cone. Just turn sideways, but. So,
That is
So
so
So the
cool.
volume of that, yeah, it's pretty interesting. So that's a proof of the well-known cone formula. So, yeah, the cone turns out the cone has exactly 1/3 of the volume of a corresponding cylinder. Right? If it was a cylinder, it would just be pi r squared times height. Okay.
That's so cool. This is why I love math. Like, that's amazing how that's been something we were just given at one point in like and we just had to be like, all right, I guess that's true. And now we know why it's true. That's so cool.
Our thought processes are very different because
You
I'm
talk
just
about the
okay
other
with
one.
being
The-
ignorant about
That's like calculus is really what makes it interesting. Is it lets you prove a whole bunch of like results that, like for example, the area of a circle, for example. You can make some you can make some arguments that are pretty solid that don't involve calculus, but if you want to get precise, you got to like use calculus to
Yeah,
prove that's
that's
correct.
so cool.
And so anyway, I like so hopefully I like the next one too. The next
Yeah.
one's very similar. What shape for B? What shape does it describe if you go y equals the square root of r squared minus x squared?
Ellipse.
Semicircle,
So,
where the radius is r. You understand that? So let's revolve this around the x-axis. So what shape is that going to form? Sphere. So let's examine one of these slices. This one looks pretty
Isn't it
good.
a ball?
We're not going down that path again.
Well, back to what you were talking about before, the way it's phrased, it just says, what if you revolve the curve around the x-axis? Then it would be a sphere. But if you're revolving this region around the x-axis, then it's a ball.
Winky winky.
Okay, so imagine this little slice revolving, carving out its disk. So hopefully you can imagine that sphere being constructed, bunch of disks. So let's examine the disk. Okay, what's the radius of our disk? The thickness is dx.
Oh, sorry.
Thickness is dx, which of course clues us in that I want this thing, I want to have x's in it. I want x to be my variable that's showing up. And so the thing of this radius, isn't that just the y value of this point, right? And the y value of that point is the square root of r squared minus x squared. You okay about that?
Yeah.
Okay, so let's set up the volume of this would be pi times the radius squared times the thickness dx.
Oh, I should probably leave myself room. I started writing in the middle of the page. Doesn't make any sense. What are you talking about?
Okay, and then we gotta integrate, right?
Yeah.
So what's our bounds of integration? We could go 0 to r as long as we do what? We could double the whole, so that's totally fine, because it's symmetrical. The right half is the same volume as the left half. All right, more scary stuff, although, wait a second, this is
Not
actually gonna be
scary.
super easy because all that's left over is that, and don't let that scare you either. What is that?
A constant.
That's a constant.
It's like 3 minus x squared.
So yeah, so what's the integral of this term?
Um,
R squared.
R squared times X. Do you feel okay about that? Yeah, because it's a constant, so if that had been like a 6, it'd be 6X. And then this guy over here is
Cubed over
1/3
Oops.
X cubed. And we're gonna evaluate from 0 to.
I thought if it's a constant, you could put it on the outside.
Well, if it's multiplied.
Yeah, so like,
Yeah.
for example, like
Distributed
the integral of 5 times x squared is the same as 5 times the integral of x squared.
Okay.
What we have here is more like an addition side. Okay, so let's plug in, being really careful. Plug in the r to both of those. R squared times r is r cubed. Put r in there, you get 1/3 r cubed. And then minus, we gotta plug 0 in. 0 just gets us 0.
This is zip.
And now,
This
a
bar.
little bit of banana action.
Look at this bar. Banana.
Banana minus 1/3 of a banana
It's 2/3.
is 2/3 of a banana.
That's what my mom is doing. Did you ever see that?
And there we
Yes,
go.
you did.
You get the famous.
Did you see the thing? Yay! Oh, that's so cool.
There you go.
No, I
Proof.
love it so much.
Yeah, so you can use proof. It's beyond the scope of this class, but in calc, if you take calc 2, you learn about doing like surface area integrals. So you can like think about revolving this around the x-axis, but talking about how much surface area would you generate.
Wow.
You can prove, like the first sphere
I
is
always
4.
think 4/3
4 pi
is
r
a
squared.
strange one.
Okay.
This is my
Anyways.
favorite thing we've done yet. I think.
Okay.
Well, I mean, I love a lot of the things we do, but I think this is my favorite. It's
Even
so
Babbage
cool.
beats
Okay, Babbage is the best.
Anyway, to explain this, so